Hello, this is my first video about sheet metal design in Autodesk Inventor. So a friend of mine has asked me to show him how to design a mild steel or aluminium enclosure, so sheet metal parts in Inventor. So he's been buying these in and putting guitar amplifiers that he manufactures into these parts. And he's paying about £30, so 30 British pounds for these parts. Which I think is massively overkill. They're coming in at 0.9mm mild steel and they're not very big. So I think we could probably produce these in the UK for less money to a custom size that he's paying for now. So looking at the part that we're going to design, not a particularly complex part here. I think these look like spot welds. Yeah, these are spot welds here. Underside, yeah, so flange up, return flange, mitered there. This is not a complex part. This is something that we can do in Inventor very, very quickly without any sort of difficulty at all. So Inventor, first thing, we want to find our sheet metal defaults here. So we're going to open this. So I'm assuming that you haven't set up any of your sheet metal rules so far for this. So we're going to create one now. So I'll wait for that to load. Right. So we're going to do this out of 1.2mm thick mild steel. So first things first, sheet metal defaults when we're in the sheet metal IPT. So you can see the ones that I've set up previously here. We're going to go and click on this pencil icon. We're going to create a new one. So you should have a default millimeter or metric profile here. I'm going to create a new one here. New style, copy of this. I'm going to call that 1.2mm mild steel. So set the thickness 1.2. Miter, rip and seam gap, we'll keep that set at thickness for now. So that's fine. Keep the default K factor. That's going to change based on the press brake tooling that you're using. So the punch and the die. So if we have a look at that now, we can see some examples here. So that's quite a good example. So you've got the punch coming down into the die, and when you're buying this, you will get diagrams which explain what the bend allowances are going to be for that. There you go, some good examples there. Some examples of gooseneck tooling here, but this is all academic for the most part at the moment. So we'll keep the default K factor. It's close enough for what we're doing. So we'll save and close. And then that appears for us now. The thickness is correct. Material, sheet metal rule, that's fine. Default K factor, fine. Okay. So we'll go ahead and we'll save that now because that's going to save our template for when we create a new part. So new, and we're opening that sheet metal IPT again that we've just created our 1.2mm sheet metal rule in. Oh, don't worry about that. There we are. Right, so first things first, we have nothing on the screen. We're going to start with a 2D sketch, as we usually do with sheet metal parts. So we're going to draw out what is going to be the top of the enclosure. So let's say it's going to be 150mm and then 200mm. So we can see that's creating our rectangle there. Just press return. That's going to lock those in. So now if we wanted to change those, we just click on that and set that to 250 or changing it there. And we can do that at any point during the design process. So we've got a sketch, we can go sheet metal and face, and that's going to take our 2D sketch and turn that into a 3D sheet metal part. So follow the defaults. It's already set to 1.2. We'll look at that in a sec. So we'll hit apply. There we go. We've got what's effectively a 250mm by 150mm flat rectangular piece of sheet metal. So we've set it to follow the default, but this is where we can set what the default is. If we wanted that as stainless, we just change that to 8mm stainless. But we're going to be designing this out of 1.2mm mild steel. Use the thickness from the rule. There we go. It's going to unfold. Perfect. Okay, so everything's there. Everything in sheet metal is either a face or a flange. So if we go back to this, we can see that we need to add a 90-degree flange coming straight up. Let's go to that. So we go sheet metal tools, flange, 1 flange, 2, 3, 4. There we are. Perfect. I'm going to hit apply. So we can see we've got there, that gap is going to be set at 1.2 mil as defined by the rule. But what we can do here is if we double click on the flange on the tree on the left, go to corner, gap size, we can set that as 0.1, and that just brings those in nice and tight. I think for the sake of easiness when it comes to folding, we'll set that at 0.5. There we are. So we've got the bulk of the enclosure there. If we wanted to change the depth on the flange, we could set that to, I think, probably 50 mil. No, yeah, 50 mil. So there we are. So we've got the bulk of the enclosure there. So what we're missing is going to be this return flange here, and this is mitered in. So we'll go in and add that now. So sheet metal tools, flange, and we need to make sure that we select the inside vertex there. And that's going to auto miter for us there straight away. But we don't want the flange to be that deep. So if we set that about 15 or 10 mil, that looks about right to me. Brilliant. And if we look at the gap size there, so that is that. And we'll go ahead and we'll match that to this here. So it creates a consistent gap. Hit apply. Yeah, there we are. So if we're looking at that gap there and that gap there, that's both 0.5 millimeter. So on a 1.2 mil mild steel stock, that's absolutely fine. That's not a problem. So as we've designed a sheet metal part, we can go ahead and we can look at the flat pattern. So we'll click create flat pattern at the top. And that's what we're expecting. We've got our corner relief here, bend relief. We can see our folds for the flanges. And that's exactly what we're expecting to appear. That's fine. We'll go to folded part. There we are. So for an enclosure, we're going to want some way of mounting it onto whatever it's going to be mounted to. So we'll start a sketch and we're going to select this flange here. So any one of those 1, 2, 3, 4, any one of those 4 there would be absolutely fine for this because they're all on the same plane. So we'll draw in a circle. We'll set that at 3 mil. We'll go again. 3 mil there. So when you're creating sketches, we always need to dimension. So we'll dimension from the center of that to the edge of there. And we'll set that 7.5. Oh no, too much. All right, so that flange is 10 mil. So 5 mil, we'll position that between there and there, totally central. So we'll dimension again, 5 mil again. And then we can set the dimension between those at 100 mil. And then dimension from that top edge there, put that 25 for now. This is going to create a driven dimension here because it's already set. So when you see something in brackets in Inventor, it's a driven dimension because it's set from there and it's set from there. So it could not possibly set its own dimension. It's informed by the others. So we set 25, 25, 5, 5. So it's going to be equal. So if I create another dimension here, it's going to show up as a driven dimension. There we are. Same thing again. 5 in brackets. Okay, so then what we'd go and do is create the sketches over there. In the same sketch, we can add in the circle there, circle there, circle, circle, circle. Or we can copy and mirror, but for now let's keep it simple and we'll say we'll put in the circles there. So finish your sketch, sheet metal tools again, and we'll cut. So we want to select that, and if you'd added in your others, you'd select those as well at this point. So the extent of a cut is how far it's going to cut. Might sound a bit daft, but we'll go for thickness because it's only going to cut through the thickness of the flange. If we chose all, it would project. You can see that arrow there showing the direction that the cut is going to project. That would project then the cut through here. There we are, which can be quite useful for aligning rivet holes, etc., or any sort of mechanical fastening. You can just add in your sketch and then it will project straight through and it will keep the alignment. But we only want to go through the thickness, so extent, distance, there we are. So there you've got all your fastenings to fasten the enclosure. That's fine. We want to add something to add in all your control knobs, etc. It's one of the benefits of having these parts laser cut instead of buying in enclosures and drilling them is that you can get precise cuts and repeatability every single time. So we'll start a 2D sketch, and this time instead of selecting the face under here, we're going to select the face here. So this flange is where we want to apply this sketch to. And we can see that it's already oriented it there, so we're totally flat and square on. So he's going to want, say, 24 mil, something for an XLI. I suppose that's about that. We'll put another one half that. There we are. So then, same as last time, we want to dimension. And we'll select the center of there, and we'll go right from this edge here. We'll put that at 50 mil. And this one we'll put over here. Now this is all the sort of stuff that you're going to line up based on whatever you've made. So we'll go from there to there. We'll say 25, because that's a 50 mil depth on that flange, 25 there. There we go, just the same. So this is where you can spend all your time getting everything lined up just how you want it, based on your requirements. So sheet metal again, cut, select the centers, distance, thickness, cut. There you go, so you've got your fixing holes here and you've got your mounting holes here for whatever you're putting on. And you can apply this same method here to any one of these faces and it will create it. So we've got a flat pattern, there we are, just as we expected. Everything lines up fine. If at this point we wanted to change the material we were working with, say we wanted to go to 2 mil stainless, all we'd do, change the sheet metal default and hit apply. And everything's still the same, it's still going to be dimensionally accurate. Everything's absolutely fine. So the benefit of setting up your sheet metal rules in advance and designing with that in mind is it only takes 2 clicks to change what you're making out of. So if you find out that your stock's actually, half a mil thicker than you thought it was, it's no real hassle. Straight away, 2 clicks and you're done. So we'll save this part as the demo enclosure. So we have our part. We need to send this out for manufacturing. We haven't got fiber and CO2 lasers in-house that we can use or press brakes, so we need to make a drawing. So we'll go File, New, and we've already got a predetermined template here that we use. There we are, Durham Engineering. So we want to place a view, and we want to place a base view, and it's going to bring this up. So if we click on any of these points here, we can set it in any sort of orientation we like. So we'll provide, there we are, or we can go custom view orientation. Then that'll bring this up and we can put it in any sort of orientation we like. So we'll give it there, change the scale, make the most use out of the page that we've got. And we'll set it so that we have the hidden line visible. Okay, there we are. So we can see the internal flanges there. Just makes it easier for everybody. We're going to place a new base view, and we've already created a flat pattern. So we'll click flat pattern. There we go. Change the scale and press return. There we are. So we have a flat pattern. This is what they're going to use to fold it. So the information we're missing here, we need dimensions and fold angles. So we'll go to annotate. Annotate, sorry, A, B, there we are, bend. So that is a bend, that's a bend, 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 bend. So you have 8 folds that need to be made there, but really you've just got 2 different folds 4 times. So we're going to add in a dimension, so annotate, dimension. So press breakers are going to hit this fold first, then this one, this one, this one. And then this one will fold against that. So they're going to push that up against the backstop of that fold already. So you don't want to give them that dimension from the fold line there to the edge there, because that's not much use. What they want is that fold line there to that fold line there. And because all the folds are identical, we'll only put those 2 on. That's fine. What we'll also put on is dimensions for these holes, because they may punch them or drill them, whatever. They'll likely just laser, but make sure that we can get a 24mm hole and a 12mm hole every time. We also want to add in some text there. So text, it's 1.2mm mild steel. Let's say we're going to send initial run of 5 off. We'll put that in the middle there. We'll save this drawing. There we go. So we've got a flat pattern drawing here that they're going to be able to fold it to. They've got an isometric view there so they know what they're folding. The only thing that we're left missing is we're going to supply them with a DXF. Industry standard, they're going to use that to program it. So we'll go to flat pattern, and Inventor, this is a great feature. I'm going to right click on it and export face as. And we'll save that as demo enclosure. And that's going to export as a DXF. We can open that in TrueView. And this here is exactly what they're going to receive. And they'll know what to do with that. They can nest that in their nesting software and get those cuts as efficiently as possible. Then they'll take it over to a press breaker, get that folded up there. Perfect.